Hello everyone, this is the Robotic Hand System project. I'm Jiaxuan Li, and this project is advised by Professor Carlos. To start off, here's a video demonstration of how what is this project. As the video demonstrates, the main objective of this project is to replicate a biological movement of a hand to a mechanical output on a robotic hand. So the robotic hand is capable of holding some objects. So this system consists of input measurement device system and also a mechanical output system. As a background, there's many joint and many type of movements in the hand. This project mainly focuses on the flexion and extension motion of thumb, index finger, and middle finger. Interphalangeal joint A and joint B can move independently, regardless the motion of the rest of the hand. Joint C cannot do so. Joint C is driven by joint B. Therefore, the system is focusing on measuring the rotation on joint A and joint B, also to replicate independent movement of joint A and joint B. And here is the input system. The input system consists of mechanical linkages, potentiometer, and a glove. The function of linkages is to transmit the biological movement from the finger to the knob of the potentiometer. The potentiometer is the measurement instrument. So when the mechanical linkage drives the knob on the potentiometer, it changes the potentiometer's resistance value. The resistance changes within the potentiometer is proportional to the rotation of the finger joint, and that is how the measuring achieved. To process data and give an output to servo, Arduino Duo was used as a controller. The potentiometer is a measurement instrument, and the servo motor is the output device to create motion on the robotic hand. And here is an oversimplified circuitry. Once the controller glove picks up a motion in hand, the Arduino reads the data from potentiometer, and then the program calculates the data and convert it to desired output for the servo motor. Then the Arduino gives a pulse width modulation output to the servo to actually control the servo. The system has an overall resolution of 1.5 degree and tolerance of plus and minus 3 degree. The main constraint on the resolution and tolerance is due to the imperfection in the 3D printing components and also the unintended elastic deformation on the glove. And here is a detailed process flowchart of how the data processed in the system. First off, the finger make a movement. The linkage pick up the movement and transmit the movement to the knob of the potentiometer. Rotating the knob on the potentiometer change the resistance value on the potentiometer. Arduino then pick up the change in the potentiometer, and then the program convert the analog reading to the biological degree of movement in each joint. The program then determines if the input is valid. If the input is valid with no error, then the data further convert to the desired output on the servo motor. The program then judge if the desired output is within the physical limit of the output system, which is the robotic hand. The purpose of that is to preventing the system damaging itself. Then the Arduino give a pulse width modulate output to the servo motor. The servo motor then drive the linkage and pulley system in the robotic hand, therefore create a motion on the robotic hand. And here is the 3D model of the output system. It demonstrates the system consists of suction components, 3 pulleys and wheels, and 2 4-bar linkage on each finger. The thumb has only linkage. And here's the detailed explanation of the kinematics. For input system, as the diagram demonstrated below, when a finger joint rotates, the finger drives the linkage system and the linkage twists the knob on the potentiometer. Doing so changes the resistance value of the potentiometer that could be picked up by Arduino. And following by image analysis that compare the biological joint location and the analog reading. And then a mathematical expression can be developed to describe the relationship between the biological location and the analog reading. The mathematical expression then further used in the program to calculate the biological movement and the desired output. And here is the kinematics of the output system. The rotation motion on joint A is created by one of the servo. The servo is connected to a drive crank. The drive crank then drives the 4-bar linkage that create a rotational motion on joint A. Doing so, we also change the angle of the pulley system showing on the below. To compensate that, every time joint A has a movement, the pulley system will rotate accordingly to compensate the changes. For joint B, the rotational motion is created by another servo. To transmit the rotational motion on the servo to joint B, an idle wheel was placed on joint A, and a ball bearing is placed inside the wheel to reduce friction. The motion on joint C is created by another 4-bar linkages, which is driven by the motion on joint B. And here is the animation demonstrating how joint B, joint C, and joint A moves. As you can see here, each joint is controlled by two separate servo. Here is the dynamic force output on each joint. The data is obtained through experiment. The data is obtained through measuring how much each joint could elongate a spring. And as the spring constant is known, and also the original length of the spring is also known, we can use the reference at the background to use image processing to measure how much the spring get elongated, and then through that we can calculate how much force is output on each joint. And here is the FEA study of the critical component. The FEA study shows the stress concentration, also demonstrate how the stress going on the component. Notice that the FEA treating the component as a uniform solid. However, the 3D printed pieces I will be using has layers and also patterns of structure. So the load path is different and the stress concentration is different from FEA study. The FEA study is to provide a reference. And this is the video demonstration of the movement replication. Here's demonstrating the measurement and output of a single joint. And this is demonstrating the measurement and the output on a combination of two joints on each finger. And here's demonstrating the continuous movement on the finger and the controller glove. And this is the demonstration of all 3 fingers moving together. Here is a video demonstration to show the system is capable of holding an organic shaped object. Here is demonstration of holding an organic shaped object in a different orientation. And here is showing how the drivetrain system works. And this is the bill of material. The system roughly costs $220. Special thanks to Professor Carlos to inspire me of this project and also give me general advising and also acknowledge me to do analysis and all that other stuff. Also, special thanks to Chris that acknowledged me about the electrical system and also give me advice on circuitry design and coding design. For the future improvement, one thing you can do to minimize the system latency is to use a better companion unit such as a Raspberry Pi or a computer or like a multitask programmable chip. Also, to minimize the noise in the system, one thing you can do is to use a much better potentiometer or higher resolution encoder. Also, to higher the resolution and lower the tolerance, one thing you can do is to use injection molding to replace a 3D printing component or using a fine machining components to replace the 3D printing components. And also use a better material on the glove to minimize the unintended elastic deformation on glove that create a noise in the system. Last but not least, some components could be further redesigned based on the FEA study to make the component more durable and reduce the material use in the system. And with that, that concludes this presentation. Thank you all very much for your time. Any questions?